Hello everyone. Today I will present a simulation-based study of electromagnetic shielding in polypyrrole composites using the ASTM D4935 framework and MATLAB as simulation tool to evaluate frequency-dependent shielding behavior. Electromagnetic interference is a growing concern in high-frequency wireless systems, especially in 5G and future 6G devices, which are expected to be densely integrated. Traditional metallic shields, which are used and have been used until now, are effective, but they are heavy and they are inflexible. So we thought to consider conductive polymer like polypyrrole, which is lightweight and conductive. And of course, from recent studies, polymers are being considered. So it would be an attractive alternative. Many studies rely only on experiments which are time consuming and they are costly. So we thought that using MATLAB, which is a very useful and strong tool to model the ASTM D4935 geometry, would be a nice and strong approach to fill that gap by providing a computational model. And of course, there are no unified simulation framework for polypyrrole shielding behaviors in different frequencies. Our objective is to simulate shielding effectiveness of polypyrrole-based composites. So we will use different composites which have reported in recent literature across 30 megahertz to 3 gigahertz, aligning with our model ASTM D4935 modeled in MATLAB. We will compute S11 and S21 parameters and derive the shielding components, and we'll also compare the different composite types like films, foams, and hybrids. What is ASTM for the ones that don't know? It's a standard testing method for measuring electromagnetic shielding using coaxial transmission lines. Between port 1 and port 2 is placed the sample, in our case the polypyrrole-based composite. It has a defined geometry and is standardized for measurement of the reflected and the transmitted wave. We will evaluate the reflection loss, the absorption loss, and the total shielding effectiveness. From the shielding theory, we will measure the reflection loss, absorption loss, and multiple reflection. And for values above 15 decibel, SM becomes negligible, so the multiple reflection can be ignored. So mainly, we will discuss the electric losses based on all what we said until now. The models used are the percolation model for the electrical conductivity, the Debye relaxation for the electric permittivity, and for the magnetic permeability. Since pure polypyrrole is non-magnetic, we have assumed that the magnetic permeability is almost 1. Here you can see the geometry that we have used in MATLAB. 50 ohm coaxial line has been used with a 3 millimeter fixed gap. These are defined, are fixed from the geometry that ASTM uses. And in this configuration, we have placed the sample between port 1 and port 2, as we saw previously. The method ensures consistent sample placement, defined geometry and standardized measurements, so we don't have problems with this part. A circular sample is inserted between the two coaxial ports, and the virtual network analyzer sends an incident wave that measures the reflections and S11 and transmission S21. Shielding effectiveness is then computing using these parameters. Here you can see the flow chart. So firstly, the parameter is initialized. We have assigned material properties and modeled them. We have specified field parameters, formulas for the derivation of S parameters, and then of course computation of shielding components, numeric stabilization, post-processing and visualization, and the validation of the parameters. First result, we analyzed frequency-dependent effectiveness. We can see that the variation of the frequency from 30 MHz to 3 GHz. At lower frequencies, reflection dominates due to impedance mismatch, while at higher frequencies, absorption becomes the major contributor. Result number 2 is the effect of conductivity and thickness. As expected, increasing conductivity or sample thickness improves shielding effectiveness. Even moderate increases in conductivity leads to measurable improvements, confirming that polypyrrole's tunability as a shielding material is okay. It's appropriate. We have also compared different polypyrrole based composites from recent literature. The polypyrrole titanium-based hybrid shows the best performance, while polypyrrole films have sustainably lower shielding effectiveness due to their reduced conductivity. We have also a table here to evaluate the sensitivity to the dielectric permittivity. Permittivity, as can be seen, has almost no impact on the shielding effectiveness of polypyrrole-based materials, composites, in this frequency range. This suggests that conductivity and thickness are the dominant parameters, so the ones that control the material optimizations. These results validate that polypyrrole-based composites can achieve competitive shielding performance when conductivity is sufficiently high, and the ASTM line simulation allows fast design screening without requiring physical prototypes. The reinforced polypyrrole composites with hybrid fillers achieved higher shielding level, often even surpassing the 5 to 15 decibel. This enhancement arrives from multi-mechanism attenuation, so it's from the way that they were synthesized. It's important to say again that permittivity has almost no influence on the shielding effectiveness, and the most important part is the thickness and the conductivity. We are thinking of integrating polypyrrole coatings in antenna or wearable system and validating also the model with experimental data. Also by extending the simulations above 6 GHz for the 6G related applications. Thank you very much.